Okay, so we're starting here on section 4.8, which is an application section on algorithms. Now, I know this isn't in the schedule. I like to cover this section because most of you, if not all of you, are computer science majors, and so this will be a little bit more interesting, like the circuit section was, to see an application that you are familiar with. So because I know that a lot of you are going to be familiar with algorithms, you've used algorithms in some of your programming classes, if not all of your programming classes, we're not going to focus so much on the nuts and bolts of algorithms. Really what I want to get to is just get a common base between all of us of what words, the vocabulary that our book uses, and then get to two common algorithms in mathematics that we use all the time and we've been using since you were very young. And we want to look at those in this sense. How is it an algorithm? What's the process that's happening mechanically that we just know intrinsically? So we have three objectives out of this section. The first is to look at algorithmic language. Algorithmic language. So this is just the terminology that our book uses, even if it's different from what you've used in the past or one of your professors used. I want to make sure that we're not getting confused. We're going to look at notation. So again, the notation of this book might be different. I imagine it's not. It's fairly straightforward. It's the same notation I used way back in the day when I did my programming and computer science classes. And then the two algorithms I want to focus on are the division algorithm, and the Euclidean algorithm. Euclidean algorithm. So let's start with the language and make sure that we're all used to the same terminology. And by all of us, I mainly mean that we as individuals are used to what the book uses. So variable in algorithmic language is our storage location. In the memory. So whatever is tracking the thing you're looking at, that's your variable. Our data type is our domain of the variable. So you're used to this, its data type would be like float or long or integer or maybe string, right? It's whatever you are going to be putting into your variable. The assignment statement, statement doesn't have an extra T there. This is something that looks like x colon equals e. So I've used this term before. I said it was defined as or assigned as, but this reads as x is assigned to be e, or defined as e. I read it as defined as. In math, we say defined. In computer science, it's probably assigned. And then finally, the last thing is our conditional statement. So conditional statement, same definition that we've been using, but in algorithms, this is just telling our program or us, if we are executing the algorithm, to execute a specific sequence of events. Specific sequence of events based on a condition. So we know in programming we can't just have if-then, because if we fail the if-then statement, we get caught in nothing. Our program, our algorithm doesn't know what to do. So hopefully we've seen if then else statements. And this gets around that. So in an if then else statement, first we look at our condition. So the condition is evaluated for some value, some specific value, not just any value. Then if the condition is true, condition is true, then, this is the then part, a series of events is executed. If condition is false, then a different series of events is executed instead. Right, so you're looking at a conditional, you plug in a value for your variable x. If the condition you look at is true, then something happens. If it's not true, then something else happens. Sometimes that can be pushing it into a different conditional. Sometimes that can be just halting it and making sure it stops and say, okay, move on to the next statement. But in both of these cases, in 2 and 3, once the events are executed based on your condition, you move on to the next algorithmic statement. So maybe that's another if then else, maybe that's a different type of statement, but it moves on from there. So let's just fiddle around with some algorithmic language here in an example. And as I said in the last video, I recommend on these examples when I write them out that you give them a shot and then take a look at my answer. Make sure you pause it because I'll just keep working through. So we're going to look at 2. And so we're going to have if x is greater than 2, then y is defined as x plus 1, else do x is defined as x minus 1, and y is defined as 3 times x, and then we'll have our end do here. And in B, we're going to say if x is greater than 2, now first I want to start with define y as 0, then if x is greater than 2, then y is defined as 2 to the x. We're just going to track a couple things and see the difference between these two. So let's say in part A, well, we're going to check the same numbers in part A. But for A, we're going to look at x equals 2, and we're going to look at x equals 5 and see what happens. So x equals 2, is x greater than 2? No. So then we are not in the then statement, we're in the else. So we're going to set x equals x minus 1 or 2 minus 1, which equals 1. And then we're done. Our statement ends. For x, we need to set y equal to 3 times 1, which equals 3. So now we're done. And then for x equals 5, we are greater than 2. So when we do that, we're going to define y as x plus 1, or y equals 6. So you can think of these as ordered pairs as their outputs. So in the x equals 2 case, our output is going to be 1, 3, and our output for the x equals 5 is going to be 5, 6. I'm sure you guys have seen something like this, but we're just fiddling with it. And really we want to see the difference between the if-then-else versus just a classic if-then, a logical conditional. So we'll track the same two x values, 2 and 5, for part B. So for 2, when x equals 2, we are not greater than 2. And so the only thing that we have is that y is 0. And we get 0, 2, or 0, 2, dyslexia, 2, 0. Because our algorithm defines y as 0 to start. So when x is 2, we fail this conditional. And so this is all we have. When x equals 5, we are greater than 2, so y is still defined as 0. And then our conditional kicks in, and now we redefine y as 2 to the 5th. And so y equals 32. So you can think of 5, 32 as our ordered pair out of this scenario. Now I'm not saying the output are these ordered pairs, just to be clear. The output of each of these at the end is a y. Now this one here will give us a new x, but this conditional doesn't tell us anything about x. So again, I'm not saying that the outputs are the ordered pairs, but you can just kind of compare what happens. All right, so when we input 2 into both algorithms, the first one gives us 1, 3 as our x and our y, and the second one is 2, 0 as our x and our y. And then when we input 5, we get 5, 6 and 5, 32. So just fiddling with some algorithms here. Okay, so the next thing we're talking about are loops or iterative statements. Iterative statements. Loops. So we want to use these, as we know, when we need to do repeated processes. We don't want to have to initialize a new if-then-else over and over and over and over again. So we are going to, first say this is used for repeated algorithmic statements. That's why they're loops. And we're going to look at the while loop and the for next loop, or a for loop. So while loop, our construction, while in parentheses, condition is true. We do some stuff here, so we're going to put just generic algorithmic statements. And then we end the while. So our algorithmic statements continue on until our condition is no longer true. Right? We've seen a while loop. It just keeps spinning itself until we get to the point where this is no longer true, and then it stops. It halts itself. And then the other loop is the for next loop. So this starts with, need some more space. Let's scoot this up. So 4, and some variable gets defined. I need it right bigger, don't I? And this will be the initial expression to the final expression. So we're setting up a domain. Then after that, we would have our statements that get looped. And then we would have a next. And this is the same variable. So this might not be the construction that you're used to. I think while loops are while loops no matter what. In this case, the for next loop, the for loops, they're pretty common and they get used all the time. So much so that even I, who don't do programming, understand how they work. So let's just fiddle around with these just to play with them a little bit. We'll go quick, and then we'll get into the algorithms I want to talk about in this section. Our division algorithm and Euclidean algorithm. Again, do the example on your own. Pause the video. You know what to do now. So we're going to let I be defined as 1, and we're going to let S be defined as 0. And we're just going to trace our outputs. The output so while I is less than or equal to 2, we're going to define S as S plus I, and we're going to define I as I plus 1, and then we'll end the while loop there. So it's just a number tracker. I is our index. It just tracks up. So first, I is 1. It comes through. It's less than or equal to 2. Yes. So I is 1. S is 0. You can think of our program doing this little check. Absolutely. So S becomes 0 plus 1 or 1. I ticks up to the next index, I plus 1, or 1 plus 1, 2. And then now we have a new I, so we run the check again. Is 2 less than or equal to 2? Yes. So S becomes I plus 1, or I plus 1. S plus I plus S. So that's 1 plus 2, which is 3. I ticks up to the next. 2 plus 1 is 3. It runs the next check. This is not true. So our final outputs, I is 3 and S is 3. Just a quick. Just quick little working with the algorithm. Excuse me for coughing. I keep forgetting that I'm recording. So let's talk a little bit about notation for algorithms. So when we say notation for algorithms, what I'm talking about is if you're going to write an algorithm out for someone, there needs to be very specific things, and we typically have 5 key things that need to be there. So obviously we need the name, and we need a list of input and output variables. So these variables are not values, they're just the names of the variables, right? So in this algorithm we had I and we had S. I didn't give you a name because it was just a silly little computational algorithm. We need a brief description of how the algorithm works. So what does it do? How does it work in, you can think of this as the layman version of it. We need the input variable names, or the input variable names with its data type. Data types. Got to know, are we working with real numbers, integers, rationals, all that good stuff. The 4th thing we need is these statements. That form the body. And then finally, the output variables, or the output variable names. With data types. Now, a lot of times when you see an informal version of an algorithm, it will stop here after the first 2, because that gives you the gist of what's happening. So you'll have the name of the algorithm. For instance, we're going to look at the division algorithm in a second. So you have the division algorithm, you'll list the input and output variables somewhere, and then you'll have a brief description of what you do. In a formal algorithmic notation in math, again, this could be different for computer science depending on the author of the text and your professor, you need all 5 of these things. So let's take a look at the division algorithm, how it's written out formally. So we have the division algorithm. So its formal statements, or formal version, goes like this. Given a non-negative, negative integer n and positive integer d, d is subtracted from n until there is an integer r that is less than d left. So repeated subtraction until you hit an integer r that's less than d. Then the total number of subtractions, total number of subtractions completed is equal to q. So this is the informal version of the division algorithm. This is how we divide numbers. You subtract your divisor d as many times as you can until you hit a number less than d. Your total number of subtractions is your quotient, and your remainder is the r. We know that. We've divided numbers. So continuing the formal version, our input, n and d, where n is in z, and I'm going to add a new symbol here, so z sub 0 with a plus. You can think of as the positive integers with 0 attached. So this is 0 union the positive integers. Oops, that should be a plus, not 0. This would be the singleton set. And so I'm just unioning those two things. Now, I don't know how widely used this notation is. I've seen it before with the 0 here, so I'm going to use it here just because it's a little bit easier. So this is the positive integers with 0 attached to it. And d is just in the positive integers, c plus. So those are our inputs. Our algorithm body goes as follows. First, we define r to be n, and we define q to be 0. And the reason we're defining this is because we need to have a starting point, and we know if we don't do any subtractions, the remainder is the whole number that we're going to start with. So while r is greater than or equal to d, we set r equal to r minus d, and q equal to q plus 1. And then n equals, oops, not yet. So then we end the while. Now, notice we're not talking about the subtractions because that's defined up here, what you're doing. This is kind of the main argument because our outputs are going to be r and q. Right? And at the end of this here, what happens is we have n equals dq plus r after execution. Now this is not the output because this is just what we know from the remainder theorem. Our outputs for the division algorithm are q and r, where q is in z positive with 0, and r is in z positive with 0. Right? They're just non-negative integers. This part here, n equals dq plus r, that's just bringing in outside information that we know from the remainder theorem. So let's trace the division algorithm in a quick little example, and then we'll take a look at the Euclidean algorithm. And we're going to do a little bit more with the Euclidean algorithm just because we know the division algorithm. We've been dividing numbers forever. So let's just trace the outputs. And we're going to have n equal 19 and d equal 4. Right, so we're going to have n, d, r, and q. And we're going to have 0, 1, 2, 3, and 4 hidden in there. So these are our subtractions. These are our variables. So at the 0 start, with no subtractions. N is 19, D is still 4, R is 19, and Q is 0. Now, N and D don't change, so I'm not going to rewrite them across this table because they're always going to be 19 and 4. So after one subtraction, N minus D, R is going to be 15 because we subtract 4, and that means Q is 1. So notice you can probably guess that Q is going to mirror the number of subtractions because that's what it is. So 2 subtractions, Q is still 2. R is 19 minus 4, or 11. Then at 3 subtractions, Q goes up 1, ticked up 1. And R is R minus D, because our algorithm redefines R as these values every iteration. So then 11 minus 4 gives us 7. And at 4 subtractions, we have 7 minus 4, which is 3. Now our R is less than D, and so 19 we write as 4 times 3 plus 4. Now, we as humans don't do that because we understand division and the actual operation of division, but you can see why you've always been told that division is repeated subtraction, because that's all it is here, right? We just keep subtracting our divisor D until we hit something smaller than D, and that's what we do. So, you're going to play around with the division algorithm a little bit in the homework. Let's go ahead and talk about the Euclidean algorithm now, because this one's a little bit more interesting. Now, we've all used the Euclidean algorithm, even if you didn't know that you were using it. Euclidean algorithm. So this says let capital A and capital B be integers such that A is greater than B, which is greater than or equal to 0. This algorithm computes the greatest common divisor of A and B. Or notationally, we're going to use GCD parentheses A and B. Okay, that's the classical notation for GCDs. So first, the GCD of little a comma b equals the GCD of b comma r if a, b, q, and r are integers such that a equals bq plus r and 0 less than or equal to r less than b. So that's the remainder theorem. So our GCD of two numbers is equal to the GCD of the second number and r, the remainder, if you can write a as some bq plus r. So we need this fact. This isn't part of the algorithm. I'm writing these inside because we need them. And 2, the GCD of any number and 0 is a, because everything divides 0. So let's take a look at the algorithm body. So we start with little a is defined as capital A, little b is defined as capital B, and r, our remainder, is defined as capital B. So since it's hinging on the remainder theorem, we know that it's going to be using the division algorithm. So while little b is non-zero, r gets defined as a mod b, and usually this is done by calling the division algorithm. Now, most programming language, if I'm correct here, can do the mod function, or there's a mod function that's built off the division algorithm. A gets defined as little b, and little b gets redefined as r. And then we end our while loop, and our output is the GCD of A and B, which equals little a now. So this is just our process of essentially factoring as many copies that we can out of the same thing, or factoring the same thing as many copies as many times as we can out of capital A and capital B. It's just about finding GCDs. So the Euclidean algorithm is fun. We can do some proofs with it. So let's look at how many do we want to do. What do we got? 36 minutes, a little long here. Let's see, we'll try to aim for 3 if we can get through them. So the first one we're going to do is prove that statement, the GCD of A comma 0 equals A, if A is a positive integer. So before we get into this again, you should try and do this on your own. It is possible. You're not using the division algorithm here. You're just using what we know about definition of divides. So what does it mean to be divisible by? That's that B divides A thing. And the other thing I want to talk about is why we need A to be positive. And that's because if A was negative, then the GCD would no longer be A, it would be negative A. Right? The GCD of negative 12 and 0 is positive 12. So we always need this to be positive to ensure that this fact is true. Excuse me. So let's take a look at the proof. Hopefully you are pausing the video right now to try it on your own. So we're going to let A be a positive integer. So that means that A is greater than or equal to 0, or strictly greater than 0. Since 0 over B equals 0 for all integers B, it follows that 0 equals A times 0 plus 0, or A divides 0, and we know that A divides A. Therefore, the GCD of A and 0 equals A. And that's all there is to it to this proof, because we already know that every integer divides itself. So all we need to do is form a quick argument of why that integer divides 0. And again, this is one of those things where we know that everything divides 0, so we have to make sure that we're thinking about it carefully, and it just hinges on showing that it satisfies the definition of divisibility. And it all hinges on the fact that we know that this is true, that 0 over B equals 0. Notice here that I'm not saying that B divides 0 in this statement. I'm saying that 0 over B is equal to 0. So you can think of making this B right here an A, and then you are multiplying the A over, A times 0, and adding 0, since we can add 0 to anything. But again, this statement here does not say that B divides 0. This statement says that A divides 0. This is just our definition of 0 divided by b. Right? And I know it sounds like I'm saying the same thing there, but it all hinges on strict adherence to our definitions. This is not our definition. This is what we know to be true. 0 over a number is still 0. Right? If I split 0 any number of ways, I still have 0 things. So let's move on to the next proof here. Wrong color. So we are going to prove if a and b are integers, such that a equals 0 or b equals 0, and q and r are also integers, such that a equals bq plus r, then the GCD of a and b is equal to the GCD of b and r. So there is a very specific way that we show two values, two variables are equal in number theory. So to show a equals b, we need to show that a is less than or equal to b and b is less than or equal to a. So in your homework, you may have come across this showing equality. This is how we want to do this, show that one thing is less than or equal to the other, and the other thing is less than or equal to the first thing. Because if this conjunction is true, then there's no other case but they're the same. Because a can't be less than b, and b can't be less than a at the same time. So we're going to split this into two parts, showing each of these individually. So this is part 1, or case 1. But it's not really a case, which is why we're not calling it case 1, because we're not showing two things are true that are consequences of the same statement. We're showing that two individual things are true, that this is true, and then we'll prove that this is true. So we're going to show that the GCD of a and b is less than or equal to the GCD of b and r. So let's let a and b be integers, such that a equals 0 or b equals 0, and let c be an integer, we're going to say that this is a common divisor of a and b. Well, then c divides a and c divides b. So, since these are divisors by definition, there exists an m and an n in integers in Z, such that a equals Cn and b equals Cm. Then, for Q and R in Z, such that A equals BQ plus R. Well, A being BQ plus R. So the reason we can just state this here is because we can always construct using the division algorithm a Q and an R that make this work. Right? You are always allowed to divide numbers, integers specifically. So we have A equals BQ plus R. Now we know A is Cn, and we know that B is Cm, so this is Cm Q plus R. And then we can factor out, well, not factor, we can subtract this over and then factor out, so we get C times N minus MQ equals R. So since N minus M, N, M, and Q are all integers, N minus MQ must be an integer as well. So since N, M, and Q are integers, N minus MQ is also an integer. Therefore, we have that C divides R. Because that's what this is. We have C times an integer equals the other, so C divides R. And moreover, C was arbitrary, so every common factor of A and B is a factor of R. And therefore, a common factor of B and R. Oh, I just realized, being silly, we want these to be, one of them to be non-zero. I don't know why they would need to be 0. So make this quick change. We'll go back in a second and update. But in our statement, we needed one of them specifically to be non-zero, so one of them here is non-zero. That's my mistake. Okay, so we're back down here. We have an arbitrary common factor of A and B, and we've shown that it is always going to divide R as well. So this is why we needed them to be non-zero. So since both A and B are non-zero, A and B are not both 0, the GCD of A and B isn't 0. So this is why up there we just had to make that change, that A is non-zero or B is non-zero. Because if they're both 0, then our GCD could be 0. But as long as they're not both 0, then we can ensure that this is true. So we are going to let, scooting up here, we're going to let D equal the GCD of A and B. By definition, D divides A and D divides B. So with what we proved up here, we also know that D divides B and D divides R. Now, we've said something very specific here. We know that D is the GCD for A and B. And we know that D divides B and D divides R, so we know that it is a common factor. Now, some of you might be thinking, well, isn't this the proof that it is equal to the GCD of B and R? And the answer here is almost. It's not quite, because we haven't guaranteed it, and we don't need to. All we're trying to say here is that, so it must be the case that the GCD of A and B is less than or equal to the GCD of B and R. And again, you might be thinking, well, shouldn't it absolutely be equal to? And the answer, like I said, is almost yes. There's a little bit of work that you'd have to do to extend this, and that little bit of work is more challenging than it needs to be. So now that we have this half, we have A less than or equal to B, we just want to show the reverse. So we're going to move into part 2 of this proof. And we're going to show that the GCD of B and R is less than or equal to the GCD of A and B. Now, it's the exact same setup. So you still have your A and B where at least one is non-zero. You still have your Q and R that makes A equal BQ plus R. And then we have to show that we have this inequality, GCD of B and R less than or equal to. Now, we're actually not going to do this because this is a homework problem. So I'm going to make you do it. And this lecture has gone a little bit longer than I anticipated, so we're going to pause. We're going to stop here. There is some problems in the homework that ask you to use the Euclidean algorithm, but it's just using mod. So there's a couple examples that you can look at in the textbook if you are struggling with that, or you can come talk to me in my virtual office hours. Remember to sign up. I've got 2 people signed up already, so just shoot me an email or a Canvas message. I'm checking them as frequently as I can. And yeah, that's the end.